Hey, we're here to talk about queues. And many of you may be wondering, or at least wondered when you saw the abstract for this, why? Because, queues are pretty simple, right? They sit there in between the producers, which enqueue messages, and the consumers, which dequeue messages, usually but not always in the order in which they were added. And the reason is that queues are kind of everywhere, right? If we are trying to do anything simultaneously, like for instance, handle incoming HTTP requests, we handle that in Java, for instance, by creating a thread pool. And a thread pool is just the act of putting a queue in between the incoming requests and the threads that are all simultaneously reading off of that same queue. And under the covers, this blocking queue actually has not one but three queue-like data structures inside of it. We have the buffer, which has the FIFO sort of semantics that we're familiar with, but it also has these things called conditions or condition queues. And these condition queues are called not full and not empty, respectively. And these are used when the buffer is either full or empty. If we try to add a message to a full buffer, then we are forced to park ourselves at the not full condition, which will get triggered whenever the buffer loses one message. And then one of the threads which is waiting at that condition is woken up and can proceed. And under the covers, the conditions are implemented somewhere deep in the JVM. I'm not entirely sure how, but this is built on top of a bunch of queues that run within the JVM, and the threads themselves are built atop queues that are within the OS for scheduling. And even those, when we get down onto the hardware, run on cores, which have their own sort of ability to do schedule for hyperthreading and other purposes. And so between us and everything that we want a computer to do, there are about half a dozen queues at least. And so, this is a ubiquitous structure, right? This is something that we use everywhere. And the reason is because queues allow us to separate the question of what we want to have happen from when it happens. And this is really important because outside of some very controlled environments, we as programmers do not know the context in which our code is going to run, right? We know that for a particular request, we want the sequence of events to happen. We don't know when we're going to get a request. We don't know how many requests we're going to get. We don't know what their relative priority is. And so the only sort of option that we have is to talk about this in the abstract, to say we want this event to happen at some point, and then allow the semantics of the queue and the sort of execution model of our system to determine exactly how that plays out. And so given the ubiquity of this, I think it's important for us to understand queues, how they work, how they fail. And fortunately, there's this thing called queuing theory. Unfortunately, it is mostly a branch of statistics and has very little to do with software. And this is a slightly snarky slide. I am by no means a leading expert on queuing theory, but I am someone who's taken 2 or 3 pretty solid attempts to understand it. I'm someone who's written a number of systems, and what this talk is the things that resonated for me, the things that I read and I wish I had already known. With that said, there are more sort of formal references for this. This is by far the best book that I've found. It's about 90% pure math, but it does try to ground out into sort of more real-world examples. And if you find this talk interesting, I highly encourage you to read this, because it's very likely that the things that resonate for you will be at least slightly different from the things that resonated for me. With that said, one of the core distinctions in queuing theory is between closed and open systems. In a closed system, there's only one thing happening at a time. The producer will give some sort of task to the consumer. The consumer will work on it. It will come back, and only then is the producer allowed to introduce something new. A very common real-world example of this is a shell prompt, right? We type something in, it goes away, it works, and then it delivers another prompt. Another example of this is a single person browsing a website. If someone clicks on a link, they have to wait for the next page to be delivered before they can click on a new link, right? These certainly exist, and we do build them and we do interact with them, but by and large, they're fairly easy to reason about. And so the real sort of scary thing, right, the thing that we struggle with are what are called open systems, where there's none of this sort of coordination. There's none of this ceding of control from producer to consumer. This is what happens when we open up a web server to the world, right? Requests come in, and while we're really trying to finish one, another one shows up before we're ready. This is, inevitable. And so this talk is mostly going to concern itself with open systems. And I spent some time trying to figure out how to best introduce the semantics of open systems. And it turns out that using real-world examples is not a very good way to do this, because real-world systems have not one queue, but hundreds of queues, all sort of interacting in very difficult to understand ways. And so What I'm going to do first is show you a simulation, right? This is going to be one queue behaving in a way which sort of tries to mimic how the real world works, but has all the caveats that come with a simulation. In the simulation, producers are exponentially distributed. And what this means is that the time between each event showing up follows an exponential distribution. And an exponential distribution has a very particular property, which is that no matter how much time elapses, we never become more likely to get an event. So if we expect to have people show up once every minute and then an hour elapses, it doesn't mean that we're suddenly due. There is a very particular sort of fall off to this curve. And this is a good model for sort of events coming in from people who are not coordinating with respect to each other, people who are not aware of what other people are doing. So this is a good model for how often people show up to banks or to food trucks or make requests to web servers, right? These are sort of many independent actors. When we talk about the complexity of the tasks that show up, though, exponential distributions are not a particularly good model because they have this very particular shape, which maybe doesn't model the complexity of our tasks. And so a more common distribution to use when we're talking about the complexity of the incoming tasks is what's called the Pareto distribution. I'm assuming most of you heard at one point about sort of the 80-20 rule, right? This is a particular sort of ratio, a particular type of Pareto distribution that has a ratio between the head of the distribution and the tail of the distribution, right? But for different sorts of systems, we're going to have different sorts of relationships between these sort of more common smaller tasks and the less common larger tasks. And so for the purposes of our simulation, we're going to have a bunch of arrival times which are determined by an exponential distribution. And what this means is that even if events are showing up at, for instance, 1,000 queries per second, that doesn't mean that they're showing up at regular 1 millisecond intervals, right? They kind of pile up on top of each other, and then there are long periods of time where nothing happens. And the complexity of these tasks over time is going to turn from something which is relatively thin-tailed, right? Has a lot of very simple tasks and very few complex tasks, to something which has a fatter tail or is on average more complex and also has more of these sorts of outliers showing up. And if you're looking for a real-world example of why this might happen, there are tons, right? Maybe our cache got flushed. Maybe we're now reading from disk at the same time somebody else is. Maybe there's a network issue. Maybe one of our downstream services is in the middle of GC, right? There are countless reasons why this might occur. And when we're looking at the behavior of the system, I'm going to use something called the latency spectrogram. And I don't expect that many of you have seen this before, so I'm going to take some time to explain it. The vertical axis here represents latency, or logarithmic latency. And latency is defined by the time that elapses from an event showing up, it traversing the queue, getting consumed, and being completed. The horizontal axis here represents time, and specifically the sort of transition from this thin tail to a thicker tail sort of distribution. The color represents the density, how likely it is that something sort of falls within that particular layer. And it starts with red as the most likely and falls off to sort of the cooler colors. And so we can see here at the far left that we have this very thin red strip, right? This is a system which is behaving normally. There are some things which are taking longer, but by and large, we're being able to have a very consistent, fast sort of handling of this. But as the distribution begins to change over time, we see about 2/3 of the way through it leaps up. And they start to sort of get scattered around. And this is still stable, or largely stable, right? But we're responding now maybe 1 or 2 orders of magnitude more slowly than we were before, right? We're really starting to kind of get under load. But this continues, and eventually we just sort of completely lose our ability to keep up, and we take off, right? And notice that this sort of has this very large arcing trajectory, and it's suddenly what was very diffuse became very, very tight, right? We have now a very reliably slow response. And this is because the time spent on the queue now dominates, right? Everything is on this sort of constantly growing queue. And so whereas before we were relatively sensitive to the variations, the queue has averaged it all out, right? We are very, very reliable, but growing ever more slow. And of course, this wouldn't continue forever. Eventually we would run out of memory or something, some sort of fixed resource that would cause our process to fall over. This is a system in crisis. And we know what we do when we have too much load coming in, right? We just add more machines. And so this works exactly like you would expect. If we add one more machine, we can see that it remains stable and is in fact able to respond much more quickly and much more reliably even at the sort of far left. But as it sort of continues, we see it start to flare up. Maybe if this trend continued over time, it would also fall over. When we have 4 machines, we're barely phased, right? And this is intuitive. This is something that we would expect. This is sort of how we respond to these sorts of outages in the real world. A less obvious thing, though, is what happens when, as we increase the number of consumers, we increase the rate of incoming messages by a commensurate amount. So here we see that we have 1 producer and 1 consumer, and 4 producers and 4 consumers, and 16 and 16. And notice that all of these fail at exactly the same time, which makes sense, right? That is the point at which we are sort of outstripped, no matter what the sort of coefficient here. What I think is more interesting, though, is how they behave leading up to that point of failure, right? We can see that with only 1 producer and consumer, it's very sort of diffuse and then begins to kind of grow more chaotic and before it finally falls over. In the case of the 4, it has a little bit of a lurch closer to the point of failure and then falls over. In the case of the 16, it's like almost unexpected. It comes from nowhere, right? It's behaving very, very reliably up until the point where it falls over. And sort of the intuition here that we need to have when we reason about this is that when we have an unusually complex task that comes in, things in the queue will begin to sort of grow behind it, right? If we have 1 consumer and a really unusually complex task comes in, things begin to back up behind it. And now the time that they're spending, the latency, begins to be defined not just by their complexity, but by the complexity of everything in front of it, which means that even the really simple tasks sitting behind a complex task become very slow to compute. But if we have more than 1 consumer, we're less hobbled by the fact that we have this thing come in, right? Maybe we only have 3 out of the 4 consumers to sort of make forward progress, but that's something, right? In the case of the 16 consumers, we have to have this very unusual confluence of events to actually be stuck wholly, right? And so this is important because the variance in our responses, even under sort of more typical loads, determines the stability of services which are upstream of us, right? This sort of change in the distribution that we saw that caused us to fall over could easily be the thing that causes somebody else to fall over, even if we're still behaving in a largely correct way. And I want to point out that the 16 consumer case is by far the closest to the systems that we build, right? We have multiple machines, we have multiple threads. And so this sort of sudden failure is the norm. So what we've learned so far is that your system is probably an open one. At least it is if you're worried about it. And it's the long tail, the unusually complex tasks that makes the queues fill up. And that means that when we're looking at the complexity of tasks, looking at the mean or the median is absolutely the wrong thing to be looking at, right? We need to be looking at the upper sort of tiers of these distributions, looking at the 99.9 plus sort of tasks, because these are the things that dictate the behavior of our system. And more consumers will make us robust to these sorts of outliers. But in either case, when it falls over hard, right? Because there really is no substitute for just being able to keep up. And so the one thing that we have learned from this, and if you take nothing else away from this talk, take away this. It's that unbounded queues are fundamentally broken because they put the correctness of your system in other people's hands, right? In having an unbounded queue and just sort of leaving it there, we make certain assumptions about how our users are going to behave, but we don't tell them that, right? And even if we do tell them that, they're not necessarily going to respect that. And so this is just a failure mode that we have left wide open, and it'll happen eventually. It's a given. And so it's not sufficient to just hold on to all the data. We have to have some bigger, better plan for what we do when too much data sort of shows up at our doorstep. And so the 3 things we can do are we can drop the data or simply get rid of it the moment that it shows up and we can't handle it. We can reject the data, which is to say drop the data and respond back to the producer that we dropped it. Or we can pause the data, which is to say to the producer, we can't handle this right now. I'll let you know when we can. So dropping is something that we can do if the newer data showing up makes the older data obsolete. This is true for certain forms of telemetry. This is true for a very sort of narrow set of cases. It's also true if we just don't care, right? It's great if we get the data. If not, then so be it. I think that we tend to say that this is the case way too readily. One really common example of this is that StatsD, which is a monitoring tool, uses UDP as its typical sort of transport mechanism. And UDP is a best effort delivery system. If it gets there, great. If not, so be it. And the problem here is that we are trying to understand the state of our system. And when we're most in need of understanding our system in high fidelity, we are least likely to get it because if the system is in crisis, then the data is not necessarily getting where it needs to go. And I think a lot of people tend to say, oh, it's fine, we'll just drop the data if we can't handle it, because they assume that that will never happen, right? The assumption is like, I guess in theory we might have to drop the data, but in practice I've never seen it happen. And in some cases it might be invisible to them if it's happening all the time. But if you hear that, distrust that. Right? Don't assume that it's true that this will never happen in practice. So rejecting is oftentimes the only thing that we can do. This is what happens when a server returns a 503. This is what happened when Twitter returned the fail whale back in the day. This is a system saying, I got your request. I don't even know what it means. All I know is that I can't handle anymore. Right? We do not even have the resources to more gracefully do anything than just say, go away and come back later. And often this is the only thing that we can do in an application. And the sort of semantics of that, right? Exactly how we do this, what sort of page we return, how we message this to the customer is an per application sort of decision, right? This is something that needs to be sort of discussed and designed and everything like that. But oftentimes when we build these sorts of tools, we're not building it with respect to a particular application. We're building something that we want to be able to use in a variety of applications. And in that case, we cannot make the choice to either drop or reject the data because that's only something that someone with full knowledge of what we're trying to accomplish could do. So the only thing that we can do is we can defer the choice. And this means we can pause the data or apply back pressure, right? We can tell whoever's upstream of us, I don't know what this means to you, but I certainly can't handle that. And so that tends to sort of propagate upstream until it hits some point where someone's like, you can't handle that? I know precisely what to do, right? I can drop the data. I can reject the data. I can do the thing that is sort of application specific. And this is why in the Java implementation of the queue, we had not one but three different sort of queue-like things because the puts, right, the not full sort of condition here is where things that have had back pressure applied to them are waiting, right? That is where they sit until we tell them that they can continue. And so we've talked about queues, and what I've said is that queues are useful for separating what from when, right? We can also say that it's good for addressing potentially unbounded demand with bounded resources. We can say that it's a way of putting interfaces between systems which may have very different understandings of how much work needs to be done. And these are all saying pretty much the same thing. And the point that I would like to make is that the buffer, which are the thing that we kind of think of as a queue, right? This thing with the FIFO sort of semantics, is actually totally irrelevant to any of these properties. Right? We don't need it to be able to have this sort of separation of control. And so we can make a queue that has no buffer, right? That is an unbuffered queue. And this has all of the nice sort of semantics that we have. And the reason that this is nice is because unbuffered queues are a closed system, right? This thing that I said that we don't always get, but it's really nice when we do, right? Because now we have a perfect seeding of control, right? The producer cannot make forward progress until there is a consumer waiting for it. And so in practice, we want our queues to be unbuffered wherever possible, especially within a certain process. Because it's much, much easier for us to reason about. We don't have these sorts of amplification effects that we get when one buffer makes everything a little bit slower, and that makes things a lot slower upstream, and that can happen sort of as many times as you put these queues together. And so you may be wondering why have buffers, right? And the answer is that back pressure, sort of enacting back pressure and retracting back pressure takes time. It takes effort, right? If we want to restart a thread that we set aside, we have to copy the stack back into memory. If we want to restart TCP traffic, we have to send a message across the network and wait for it to sort of spin back up. We have to read from disk or from a database to get this stuff because the time that elapses between us being ready to do work and actually having work to do is wasted time, right? It hurts our throughput. And so a buffer is useful in that it allows us to maintain a higher throughput, have a more consistent throughput. But that is at the sort of cost of having potentially a larger latency because these things have been sitting on the queue waiting to be handled. So what we've learned so far is that you should always plan for too much data. This is going to happen. You should know what you're going to do. We should use back pressure wherever possible because that is the most neutral choice, right? It allows somewhere else in the system to make that decision. And in practice, that decision should be made in one place. We don't want to have a lot of different sort of dropping or rejection strategies interacting with each other. We should have it defined in one place, which makes it easy to change, easy to understand. Buffers can give us throughput at the cost of latency. And this is something that, like the sort of choice of how to respond to this, buffers should exist in as few places as possible, right? Maybe you have one big buffer at the sort of periphery of your system, but having many different buffers makes it hard to think about, tends to amplify these sort of latency effects. If you want some more information on this, search for TCP buffer bloat. This is a very good real-world example of what having many composed buffers together will give you. And so in practice, most queues should not have buffers. A concrete example of this is a system that I worked at my previous job where I wrote a service called Ma. And Ma was sort of an omnivorous data service where people could post data to us and we would write it to a disk for later batch processing. It was very simple, did very little, just had to kind of get the data to a place where it was safe and at rest and replicated. And so all we really need to have here is some sort of thing where all the data comes in, it gets balanced across a bunch of machines, they do some minimal processing on the incoming data, and then write it to some sort of store. And because I was trying to make my life as easy as possible, we decided to build this on top of Amazon, which gives us the elastic load balancer to spread this across all there and can generally handle a lot of volume if you ask Amazon nicely. And S3, which is a perfectly good replicated data store. And so this solves a lot of the harder problems that might fall out of this. And all that was left to me is to sort of build the thing in the middle. And so some key properties about this service was that it had to be horizontally scalable. Over time, the sort of volume on this service grew from about 40,000 requests per second to about 500,000 queries per second. And this was something which just sort of had to be able to deal with. It had to be low maintenance. This was not the only thing I was working on. If it took more than a day out of every month, then something had gone seriously wrong. It was not real time. We were trying to do batch processing. The data had to get into some sort of persistent store eventually, but immediately was not a requirement. And the most important thing was that the loss of data was directly proportional to the loss of utility. This is something where we're trying to do sort of high-level pattern analysis. And so losing 1% of the data would lose us at most 1% of the utility of this data. This is very different than if we were doing payment processing, where losing 1% of the data would lose us the entire thing. And so this makes the job much easier, which is exactly what we want. And so previously, I'd sort of thrown together a little background process that would consume the Twitter garden hose, which is 10% of the Twitter fire hose. And this was consuming about 600 tweets per second at peak. And so what I did is I took an HTTP client, I piped it into the Hadoop S3 client because that's what we had on hand, and wrote it to S3. And this worked perfectly well. And so for my initial sort of V0 of this, I took a web server built on top of the Java Netty library, I piped it into the Hadoop S3 client, and we were off to the races. The problem was that I was previously unaware of the fact that S3 would sometimes stop accepting writes for a while. I don't know why, but this is a perfectly reasonable thing for a downstream service to do. What I also didn't know is that the Hadoop S3 client, in response to this, would simply accumulate messages in the hopes that S3 would become available again, it would be able to flush and catch up, and everything would be great, and we wouldn't have lost any data. But in practice, what would happen is that the queue would grow until we ran out of memory. We would start OOMing. The process would fall over. The traffic would be load balanced onto the other machines, which were equally unable to talk to S3, and the entire service would just die. And so clearly, this was not a good approach. And so when I started thinking about it from more first principles, I realized that I'd been making this job a little bit harder on myself than I had to, because we wanted to eventually get to S3. But what we're trying to accomplish over the course of accepting a request and coming back and saying, OK, we handled your little new chunk of data, was it had to go somewhere that wasn't memory. So we could write it to the local disk, and then in the background, take it from the local disk and upload it to S3, right? We just had to get it there eventually. And the fact that if it's on disk and the entire sort of host dies, then we might lose the data, but that's OK. We're OK with losing a little bit of data. We don't want to make a habit of it, but so be it. And so for this, I wrote a couple of libraries that were open sourced. These are closure libraries, so use that if that's what you use. But they're pretty simple, one of which is a thing called a durable queue, which is what it sounds like. It's a append-only disk-backed thing that uses slab-allocated files and memory mapping and other things that make it reasonably fast. And on top of that, something that journals data to S3 by first writing to the durable queue and then pulling off the chunks of work as they come through. And so this system, as it was much more stable because all we had to do was write it to disk, and disk gave us a lot more space than memory. But just because I was solving an easier problem doesn't mean that it was somehow guaranteed to work. And so arguably, one of the flaws of the Hadoop S3 client was that it didn't, ever let go of data, right? It just, kept on accumulating, had this unbounded queue that was fundamentally broken. But another flaw that it had is that it never told me that, right? There were no metrics. The only way that I could actually infer that that was what was going on was by waiting for the failure and then having to go and pick up the pieces and figure out what happened, right? There was potentially a way that it could have sort of broadcast that it was in distress, not enough distress to fall over, but still something that would have, told me that this is what was going to happen. And so for these libraries, I made sure that there were reasonably rich metrics for this, right? In the case of the S3 journal, there are some fields that will tell me how many tasks have been queued, how many of them have been successfully uploaded. For the underlying queue, it has some more in-depth stuff like how many slab files are there on disk, how many are loaded into memory. And so this is great, right? We have metrics now that tell us about the part of the process which is taking stuff off of disk and uploading it to S3. But there's still the other component, right, where we accept the data and we respond back as quickly as we can. OK, we got it. We handled it. And this is important that we're responding quickly, because if we're not doing that, then our partners were going to sort of ramp down the volume of data they were sending us, because they would assume that we couldn't handle it. And so we needed to make sure that what we were measuring both sides of this system. And one of the sort of interesting complexities here is that Netty, the underlying library, has a model where connections as they are opened are assigned to a particular thread. And this is very useful because it allows us to not have to worry about multi-threading. It allows us to use non-thread safe operations in the sort of context of a particular connection. But it also means that if any one operation blocks, it blocks a bunch of other connections that have nothing to do with what it's trying to do. And because we are interacting with the disk, then things can block, right? This is something that we should plan for. And so the solution for this is that you go and you use another queue. You put a thread pool behind this, and as requests come in off the wire, you forward them in where they can be handled by a separate thread pool, which decouples them, allows you to block on a particular request without causing a bunch of other connections to be similarly affected. And when we talk about metrics, typically the beginning of the request lifecycle from our perspective is when it finally comes in off the queue, right, where we begin to actually act on this. And a lot of request response latency metrics will measure only this part. But this is a problem, right? Because, again, queues introduce latency. We know this. And we need to be sort of aware of what's going on. But thread pools in Java are not very well instrumented. And so I ended up writing another library, which is a Java implementation of instrumented object pools and thread pools, and has some mechanisms that allow you to take the telemetry coming in off of that and use it in a feedback loop to resize the pools. And this helps a lot, because it means that whenever we ran up one of these servers, we could have a nice little JSON endpoint that tells us a whole bunch of things about the functioning of the system. For instance, it tells us the rate at which tasks are coming in, they're being completed, and being rejected. And notice that these are not single scalar values. These are distributions because, again, these things are exponentially distributed. Sometimes events show up all at once. And so if we sample this at a small enough time slice, we'll notice that for some time slices, at the 99.9th percentile, we're getting 100,000 requests per second within this little time period. But the median is that we're getting 30,000. And this is important, right? Again, we're trying to understand sort of what is the maximal load that our system is having to deal with. Likewise, we can look at the task latency and the queue latency, where the task latency is the overall time it takes for something to clear the queue and get read. And the queue latency is just the time that's spent on the queue. And you'll notice that the upper end of both of these distributions are different. The queue latency is actually a lot larger, even though that's supposed to be a subset, and this is because this is sampled, and both of these are looking at slightly different samples. But the other sort of interesting thing here is that the queue length is 0, because we are using an unbuffered queue. And yet, sometimes, apparently, it takes us 2 milliseconds to traverse that empty queue. And that's not because we're waiting, right? If the queue actually had nothing on the far side of it, we would just reject the request outright. And so this means that somewhere, even though we're not unbuffered, somewhere in the bowels of the JVM, there is a buffer. We're traversing it. We can't help it. And so you should always be clear that just because we've decided to make something unbuffered, that doesn't mean that there's some sort of instantaneous execution semantics here. And so now we have better metrics. We don't have complete metrics. We don't have something that actually measures the entire system, because the system's not just us. It's also the client that's talking to us. And maybe someone makes a request and drives into a tunnel, and it takes us 60 seconds to actually get to them. And this is something that we could measure, It's not clear what we would do with that information if we knew that people were doing this very often. But there's always more for us to be able to measure here. And so what we've learned so far is that we should be very clear about what it means to be complete in a particular task, because if we can move the goalpost closer, that just makes our job a lot easier. We should be very picky about our tools. We should make sure that they don't, for instance, have unbounded queues lurking somewhere in them. We should also make sure that they tell us what they're doing, because if you're looking at a system and you're trying to make it fast, right? You're building a system from these pieces. Building it on top of pieces which are individually fast because you found a benchmark that said they are individually fast doesn't necessarily turn into some sort of gestalt which is itself fast, because the assumptions made of the benchmarks, even if it very closely resembles what you're doing, it's not exactly what you're doing, right? And so you should always prefer something that tells you what's going on as opposed to something where you have been assured that it'll be fast, don't worry about it. And of course, you're never measuring all of your system, but you should measure as much as you can easily. And you should always have in mind sort of a next tier of things that you could be measuring if the system begins to behave oddly. So one last example here. A lot of networking frameworks, when they are trying to give sort of an introduction, will use this example, which is a chat server. Something which is a small subset of IRC or something like this. You saw this a lot with Node when it was first being rolled out. And what I'm going to use for this is a language called Clojure. You probably are not all deeply familiar with this. I don't think it's important as long as the parentheses don't completely cause you to roll your eyes back into your skull. But we're going to be using a library here called Manifold, which has a collection of sort of async primitives. One of these is a thing called an event bus, which is an in-memory publish-subscribe model, and that's really all you need to know. So our chat room that we're building here has a connection. This connection can be TCP, it can be a WebSocket, it's just some sort of duplex communication socket. And we assume that the first message that is sent to us by the client is the room that it wants to join. Once we have that, we can set up two persistent flows. We can take all the messages coming off the connection and publish it to the room. We can then take all the messages being published to the room and forward them back to the connection, right? Very simple. But this actually gets us a chat room, right? It's fully functional. But there are some problems here, right? One of which is that when we're publishing, the act of publishing is defined as successfully sending it to all the people who might be downstream of us, everyone who's listening. And so what happens if one of our members of a room drives into a tunnel or closes their laptop or does something else that makes them unable to receive messages? They are going to hold back everybody, right? Because we're only as fast as sort of our slowest link here. And so when we are thinking about this, we have to consider, like, how do we go and protect the majority of our users from these sort of misbehaving minority? And so it's not enough for us to just say blindly, let's go and connect it such that everything that comes out of a chat room is sent along. We have to potentially buffer, right? The buffer will give us some amount of control over this because it allows people to not be able to accept a message now under the assumption that they will be able to eventually, right? This gives us sort of increased throughput at the cost of latency for this individual user. And we've decided here arbitrarily that we're willing to buffer 42 messages. And this might not be the best idea because who knows what a message is? It might be a word, it might be a novel. So a better approach would be to create a metric that says how large a message is and say what the maximum aggregate size of messages we're willing to deal with here. And here we say that we are willing to deal with 1,000 units, a character, a byte, whatever. But even this doesn't really fix the fundamental problem. The fundamental problem is that we will eventually run out of space, the buffer will be full, and then we're blocked again, right? And so we have to have a hard stop, something that goes and just shuts this down. And so we can additionally say there's a timeout here, right? This connect mechanism is taking messages from some source of messages and forwarding it into a sink. And we can define a timeout where we say if we've been waiting 10 seconds for this to actually complete, then we're done. We're just going to close the connection and call it. And so that finally puts sort of an outermost boundary, right? It means that this person can only misbehave for a maximum amount of time before we're just going to go and boot them. But this actually creates a different problem, which is what happens when someone starts to send a lot of messages. They begin to spam the channel, either by accident or on purpose. And this means that now, since everybody is sensitive to this now, right? If they can't go and accept the messages at the rate that they're coming into the channel, everyone gets kicked, right? We've just set up a new sort of misbehavior. And so again, it's not enough for us to just simply take everything that someone sends to us and publish it to the room. We need to have some sort of limit on what they're able to send us. And so we can throttle it. We can say we're only going to accept one message per second. And this also leaves sort of an undefined kind of semantic here, because if someone is allowed to send one message a second and they're quiet for an hour, have they built up a credit of 3,600 messages? Is that like something that we're willing to let them send all at once? And by default, this takes the most conservative approach, which is that someone can send one a second, and if they're quiet for a while, that doesn't give them any sort of credits. But we can define that. We can say that someone gets 10 seconds worth of messages if they're quiet for 10 seconds, but no more. And so this is slightly more code than what we had before, and it has a lot more magic constants in it, right? What we had before was this sort of platonic ideal of a chat server. But the other sort of problem with this is that we can imagine this chat server is sitting in the middle of this problem space. And there are all these different dimensions here. How many messages are showing up a second? How many messages are being sent per client? How many clients are sort of misbehaving by sending 5 orders of magnitude more messages than the rest? And there are points of failure on that, right? Obviously, our system will fall over as we get to some point on that dimension. But we haven't defined what it is. We've left it sort of up to the fates. We've said, some combination of the context and the execution and the hardware that's running on and, where the planets are in alignment will cause this to fail at this point, though tomorrow it'll fail at a completely different point. And so, again, we've left the correctness of our system up to other people. And by drawing these arbitrary but hard lines in the sand, we've defined the problem that we're trying to solve. We've actually sort of carved out a space that we feel to be the problem that we want to have a good, correct solution for. And this is not to say that there aren't sort of other implicit failure modes that we're not handling. For instance, we're saying that we can handle 1 message per second from every person. But what if we have 1 billion people connect all of a sudden, right? We haven't defined that. That is still sort of a failure mode that we're leaving up to the fates. But we should always try to be as specific as we can. We should always try to demarcate as many boundaries as we can, because this gives us a better chance of having a system that we can reason about. And so we talked about queues. And one thing that we learned is that unbounded queues aren't unbounded. They're just bounded by something that we have failed to define. And when we're building an application, we should always plan for too much data. We should never allow our queues to grow without bound. But where we're not defining a particular application, we should try to be as generic as we can. And that means applying back pressure, leaving the choice up for someone else. And we should always have metrics from every part of our system, every component, subcomponent, because that's what allows us to understand whether or not the assumptions that we've made are valid. Because they're not. They're never going to be completely, right? And even if they are, then the problem sort of definition will change out from underneath us. And so the only way that we can cope with that is to actually measure things, not just limit things, but sort of measure and make sure that the limits make sense still. And so that's it. Thanks.
Questions?
It was a great talk. I guess one choice you've got is about what your defaults are, whether you go for sensible defaults. So the experience of using like HA proxy, say, where it makes you think about literally everything. How many connections are you going to take in total? How many is that front end going to take? How many is that back end going to take? At what rate are they going to come? And the defaults are actually quite low, and people get frustrated. And a similar thing happens with Hadoop, where if you start using it, suddenly you reach all these limits, and there's all these knobs you've got to tweak. But is it? I think it might be the case that forcing people to make the choice early on is better than having a sensible default that usually will work. And I wasn't sure from your examples whether you've done that or whether you actually allow people to choose rather than force people to choose.
It's the latter. I mean, so in many of these cases, there are some defaults, but generally speaking, and when you're dealing with the networking layer, where you're sort of not responding quickly enough, there will be back pressure applied and everything like that, but you're still very much able to exhaust memory or something like that. There's no automagical way to kind of detect that that's what you're doing and save you from yourself. And so I think that it is better to have a sort of dollop of documentation and education about what these knobs are and what they mean and why you should be sort of tweaking them. I think that Hadoop and some others probably hit the extreme point on this, and sometimes it ends up being a like make it work being set to true instead of false, and like that's the thing. Yeah, and I think that that's obviously very frustrating, and having non-pathological defaults is good, but I think that having people assume that whatever you set is sort of this like one size fits all kind of parameter is bound to disappoint, and so yeah.
Yeah, it was a really great talk as well. I have two questions. The first one is, with the log latency graphs that you showed to provide the example for the buffered queues, is that useful as a visibility kind of tool for general systems that we might work with day to day?
That's my intuition. I have played around this a little bit. I mean, the problem is that most people at the end of the day, they use graphite. And graphite is taking a time series of scalar values, and so doing distributions is hard. Like you can have a bunch of different scalars that represent different percentiles, but that's not quite the same thing. And so, yes, but there's a lot of complexity in kind of getting there, and it's not clear to me that all that effort is merited. Like, I don't know how much better it is, right? I've only ever used it as sort of a retrospective where you're going over sort of log data or something like that. Having it as a real-time view seems pretty neat to me, but I don't know if it's like genuinely like twice as useful or something like that.
And my second question was around, if we follow on your argument for using unbuffered queues, and to kind of annotate and use metrics to guide a lot of that thinking to understand what's going on with the subsystems that we use. Were there any common metrics that you found, whether it was runtime specific or otherwise, that you felt we should be definitely tracking and that shows some of these things? The example being the kind of latency stuff where for the 99.9th percentile thing showed up.
I mean, I think that looking at the top end of your distribution, whatever you sort of define that to be, and I think that 3 nines is a pretty common one that people use. That's useful. Another one that I didn't show on this visualization, but I find very useful, is utilization. So if you have a fixed number of resources, kind of understanding how much contention there is, how many of those are sort of laying fallow, and there's some math that is a little bit idealized, but like in queuing theory will show that once you get above like 60 or 70% utilization, the chance of collisions, where sometimes temporarily like everything will be exhausted, becomes quite likely. And so you can kind of see that as a point that gets approached, and like understand that as sort of the point at which you see that sort of drop off. You sort of hit that other equilibrium where things are stable but slower, and so that's a useful one. But I mean, I think that that's very sort of case by case, and I think it's better to understand your system and understand your metrics than sort of assume that like what worked for one will necessarily work for the other.
So you talked about queuing theory, and what I've seen of queuing theory before kind of models the world as a fixed number of executors. But we live in a sort of cloud world now where when one of your metrics goes over a certain threshold, you can start spawning new consumers. Does queuing theory have much to tell us about those more dynamic scenarios?
So yes, I mean, so unfortunately, because it is just like an idealized sort of thing, you find that like a lot of times it's modeled as like you have one consumer or you have an infinite number of consumers, and you don't have a lot in between there. And maybe the cloud services more closely resembles the infinite number of consumers than not, but it's, I mean, if I could like maybe rephrase your question, like, can you actually do formal analysis of these systems and predict what the behavior is? My answer to that would be no. And I think that it's much better to take the system as it is, stress it with some sort of benchmarking tool or something that will go and sort of put it under load, and simply observe its behavior and try to kind of intuit it from that. Like that at least is what's worked for me. If someone were able to come up with something that like could accurately simulate as I said, like the hundreds of queues that are all sort of working in tandem, that would be awesome. That would be very, very helpful, but I've not seen any such thing.
Thank you. If you have any more questions, please take them offline with Zach. Thank you for a very interesting and stimulating talk.